Hello everyone, I am Didier Ishimwe from the University of Nebraska-Lincoln. Today, it is my pleasure to introduce to you our work on Dynaplex, analyzing program complexity using dynamically inferred recurrence relations. Runtime complexity analysis can help developers detect performance vulnerabilities. Dynaplex computes runtime complexity of recursive programs by dynamically inferring recurrence relations and solving them to obtain closed-form complexity. Recurrence relations, also referred to as recurrences throughout this presentation, define the complexity of solving a problem in terms of solving its subproblems. For example, selection sort is a sorting algorithm that sorts n elements by recursively sorting n-1 elements with at most n steps per recursive step. We use recurrence relations because simple recurrence relations over linear terms are expressive enough to capture non-trivial program complexities. For instance, binary search have logarithmic complexity, Karatsuba multiplication algorithm have a non-polynomial complexity, building the Tower of Hanoi have an exponential complexity, and Babasod have a quadratic complexity. All these complexities are expressed by simple linear recurrences. I would like to take this time to give you an overview of Dynaplex's architecture. Dynaplex takes as input an instrumented program and outputs a runtime complexity in big O analysis. So first, Dynaplex runs this instrumented program on a bunch of random inputs and collects execution traces. These execution traces are the size of input and the depth of recursion per each step. From these execution traces, Dynaplex can infer recurrence relations and learn polynomial models, which then can be solved to obtain a runtime complexity. To solve recurrence relations, we use different techniques, including popular master theorem and other pattern matching techniques. This example demonstrates how Dynaplex computes the complexity of merge sort. On the left, we have a recursive implementation of merge sort in Python. We replaced a lot of statements with the skip statement for the purpose of presentation. The lines of code in red represent the instrumentation code added to collect traces. And for example, the first line shows that the traces we collect are the size of input and the depth of recursion for each iteration of merge sort. We also collect the number of loop iterations per recursive step. If we run merge sort on an input of size 223, then we get 223 loop iterations per each step of merge sort. The tree on the left shows the execution traces collected by running merge sort on a list of size 7 elements. N represents the size of input at the current depth of iteration, and ID represents the unique ID in the tree represents the depth of iteration. The number of child per node represents how many recursive calls are made per each iteration. Dynaplex computes the relationship between the size of input at the current node and the size of input at their children nodes. For example, for every left child, we have the size of input will be for, let's take the first node, will be 7 divided by 3, 3 divided by 1, 2 divided by 1, 2 divided by 1, 4 divided by 1, and so on. And this would show that this list converges to 2. And the relationship between the size of input at current node and the size of input at the right children will be 7 divided by 4, 4 divided by 2, 2 divided by 1, and so on. And this will converge also to 2. As mentioned on the previous graph, Dynaplex computes the relationship between the size of input at the current node and the size of input at its children node. We also showed that with the left ratios, the input is always almost divided by 2, and with the right ratios, the input is always almost divided by 2. Which makes the recurrence relation of merge sort become Tn equals Tn over 2 plus Tn over 2 plus Fn. Fn corresponds to the number of loop iterations per recursive call in merge sort. And we can calculate this Fn relation by running merge sort on a bunch of inputs of different sizes. The table on the right shows the traces collected by running merge sort 10 times on 10 different inputs. Using regression, we can learn that size and counter have a linear relationship, which makes Fn equals to n. Now the recurrence relations of merge sort is finally computed, and at this step we can use popular master theorem to solve this recurrence relation and obtain a closed form complexity of n log n. In this second example, we demonstrate how Dynaplex compute the complexity of Fibonacci sequence. The following tree is a tree collected by running a naive Fibonacci sequence on an input of size 6. N corresponds to the size of input, ID corresponds to the size, to the depth of recursion. The number of children per node corresponds to the number of recursive calls made per iteration. A Fibonacci program is a little bit different than the previously shown merge sort, as it does not divide the size of input by a number at each iteration. Instead, it subtracts a constant from the input at each iteration. As shown earlier for the case of merge sort, we compute the left ratios by taking the size of input at the current node divided by the size of input at the left child node. Similarly, we compute the right ratios by taking the size of input at the current node divided by the size of input at the right child node. We also compute the differences in a similar manner. From the ratios and differences, Dynaplex computes the recurrence relation of Fibonacci to be one of these two. Excuse me. The first one is discarded, and the second one is chosen because if it is correct, then the left differences will be predominantly dominated by element 2, and the right differences would have element 1 appear for more than 90% of the elements. And as we can see here, excuse me, the left differences are always 2 in this table, and the right differences are always 2 in this list. Using pattern matching, we can solve this recurrence relation to be exponential, which is the complexity of Fibonacci sequence. We solve recurrences using different pattern matching techniques. For divide and conquer programs with recurrences of the following templates, we can use master theorem. For example, Strassen matrix multiplication algorithms recurrence can be solved using master theorem to obtain a complexity of big O to the power of log 7, big O n to the power of log 7. Unfortunately, master theorem is not expressive enough to solve all recurrence relations. So we developed a pattern matching technique for solving linear recurrence relations of the following template. For example, we can map the recurrence of Fibonacci to the complexity to an exponential complexity. We evaluated Dynaplex on a benchmark of 37 programs collected from the literature and various online resources such as Okamo's 99 problem. These benchmark programs are in different languages such as Python, C, and Okamo, and they include diverse data structures such as trees, lists, integers, stack, and so on. These programs also have diverse complexity bounds such as polynomial, logarithmic, exponential, and non-polynomial. These 37 programs are all around 100 lines of code with 5 lines of code of instrumentation. We ran Dynaplex on these 37 recursive programs and collected the results in the table on the left. Dynaplex was able to compute the correct complexity for 32 out of 37 programs. However, it computed incorrect recurrences but correct complexity for 2 programs, the GCD program and the QSOT calls program. It also computed incorrect recurrences and complexity for 3 programs. And as you can see from the table, it computed different kinds of complexity from logarithmic to linear to exponential and so on. As shown on the previous slide, Dynaplex computed incorrect recurrence for GCD program. However, it computed the correct complexity. On this slide, we can see an implementation of GCD, which is greatest common divisor program. And as we can see on the recursive call, the size of input is neither divided nor subtracted by a constant. However, they use a modulus operation. So the correct recurrence for GCD program should have been this top one. However, Dynaplex is not able to compute such recurrence, and it computes the recurrence of TB equals TB over 6 plus 1. Although this recurrence is not precise, it can still be solved using master theorem to compute the correct complexity for GCD program. We are currently working on to improve Dynaplex by using fuzzing tools to generate input that can lead to worst case execution time instead of using random inputs. Since Dynaplex is a dynamic analysis tool, it does not guarantee the correctness or soundness of its result. Therefore, we are using static analysis tools to verify Dynaplex's results. We will take this time to take questions. Thank you for your time and attention.